Khalifa University in Abu Dhabi about 2 months ago. So
Ah,
I
okay.
will explain in the talk, in
Okay, I think it's time for us to start now. We already have many students joining this session this afternoon. So I would like to start today's session. And good afternoon, everyone. Let me start this guest lecture session. My name is Putu. Firstly, I would like to say, sorry, I have to make a record for this lecture. Okay. Firstly, I would like to say thank you very much, Ludo, for your kind help to deliver a guest lecture in our department. It is an honor for us to have you here. I remember that we have started talking about collaboration opportunity between Ubaya and you from last year.
yeah.
And unfortunately, your plan to visit us this year must be delayed because of the COVID-19 pandemic situation. And I hope after this, we can still develop some kind of collaborations. And then before we start the lecture, I would like to introduce our speaker today. Our speaker is Dr. Ludovic Dumay. Uh, I usually call him Ludo. He is an assistant professor in the School of Chemical Engineering, Khalifa University in Abu Dhabi in Uni Arab Emirates or UAE. And Dr. Ludo just moved to UAE from Deakin University in Geelong, Victoria, Australia. He has extensive experiences on research on the development and characterization of porous materials and interface, and also he is also interested in developing responsive or reactive interfaces allowing for sensing or reactions during separation. And today he will deliver a talk on the topic of resource recovery strategies from spent effluents, review of current practices, and a case study on spent battery waste. And during the talk, the participants or the students can write his or her question on the chat section, and I will read the question right away after the talk, and Ludo will try to answer the question. And to start the lecture, please welcome Dr. Ludovic Dumay. Ludo, the time is yours. Thank you.
Thank you so much, Putu. And again, I'm very glad to be here today, and I hope I have been able to come earlier this year to meet you guys. But I'm sure it's going to happen very soon. It's a great pleasure for me to be here today. I'm going to share my screen and start. But today I'm going to talk about two things. So everything is focused on the resource recovery, and I have a first talk on the battery spent effluent, which Putu introduced. And oops, not this one, sorry. Sorry, just too many things open there. Where do my screen is probably easier? Yes, okay. So I'm going to start with a general overview of what we have been doing in the group for the past 12 years, I guess, in Australia. And yeah, like Putin mentioned, I moved to the UAE very recently, so I'm restarting the group down there. Things have been delayed, like you can expect. When I accepted that job, it was just at the start of a pandemic, so it was a couple of months into the pandemic, so I wasn't quite sure how things would go. Anyway, and but yeah, we have managed well so far. So I have a few people starting next year, but everything I'm reporting here is obviously from Deakin, okay, from Australia. Just a quick one there. So I'm French of background. You can't really tell from my accent. And I've done all my undergrad studies and master in France, but then I moved to Germany and thereafter Australia to do my PhD. And I finished in 2012, so a few years back. And after my PhD, I did a postdoc first at Melbourne University on CO2 capture and conversion, and then moved to Deakin University under different research fellowships position. I have a joint position with Montpellier in France, professor position, and like Putu said, from very recently, I moved to Halifa. So most of my team is now still about 10 people are in Deakin, left there. I have a couple in Montpellier and a few to come in Halifa, but yeah, everything I'm reporting is really from Deakin. So Halifa University is based in the UAE, in Abu Dhabi, and we have 4 different campuses across Abu Dhabi. Brand new facilities with lots of focus on sustainability, on membrane separation especially. There is about 15 academics, 15 professors working in membrane or catalysis per se, so it's quite large. The Department of Chemical Engineering, where I sit, has 6 different research centers, which roughly overlaps with the 38 professors of the department. It's quite a large department per se, even for Australian standards. And like I said, very focused on applied processes and applied materials as well. And I was hired to develop further that aspect there. So if you, at some times later, in the near future, if you fly by Abu Dhabi or Dubai, because we are very close, obviously only an hour 20 minute drive from Dubai, let me know if you want to visit, and I'll be happy to show you around. Yeah, that's the 3 research centers I'm linked to. So I'm linked to the CIMAT, the Center for Membranes and Advanced Water Technology, the REACH Center on Gas Separation, and the CCAS Center on Catalysis. So these are the 3 lead professors on these centers. But most of what I've been doing the last, again, 12 to 14 years has been focused on the development of surface and interfaces to control the reactivity, to control the separation capabilities of materials. That's the first thing. The second thing was to engineer porosity, so pores across materials at the nanoscale, looking at how we can get isoporous materials, for instance, with very narrow pore size distributions, as well as asymmetric structures, where we can really engineer the architecture of these materials from a top-bottom type approach. In terms of specific type of materials, specific type of application, I guess, I'm not focused on anything, because I typically go for a challenge, whatever it is, and I try to find the best couple in terms of process and material to solve that challenge. But most of what we've been doing so far was in separation, membrane, and adsorption, catalysis, capture, for instance, like CO2, and a bit of sensing as well. Recently, I have 3 different schemes in Australia, and that's the 3 I'm going to continue really in Abu Dhabi, on healthcare materials, looking at cell sorting, hemodialysis, and also microdialysis to extract specific markers in the brain. Environment, and I'm going to show you some of the stuff today, mostly on nano and microplastics, as well as resource recovery, and obviously the material aspect, which I mentioned before. Obviously, most of what I'm going to show you today is on membrane separation, so I want to make sure we all have a bit of an understanding there, and I'm sure you are familiar with it, but just in case. A membrane, in fact, is nothing more than a filter, okay? It has the ability to separate specific contaminants or resources or solvents, maybe, from each other. And we have a number of different driving forces which will be applied across the membrane. And these would actually dictate the selectivity, the permeability or permeance of specific compounds, and the yield of the reaction or the yield of the separation. The materials that we can use to make such membranes, to engineer them, can be porous or dense, like I will show you today. They can be solid or liquid as well, and be made of a fairly homogeneous material, like a single polymer or a single metal oxide maybe, or it can be heterogeneous, like a composite material. And again, you can imagine here, when you have such interaction between nanoscale molecules or just mesoscale molecules and materials, you really want to control the topology of a membrane, the topology of the pores as well, in order to be able to engineer the interactions between, in terms of charge and repulsions, between those contaminants and those surfaces. So most of our work, again, is only on surface chemistry at the end of the day. So we try to make holes in stuff in a controlled manner, and we try to make sure that we understand what surface energy we have on these surfaces. These are probably the 6 main membrane separation processes which are available either commercially or at lab scale, depending. Reverse osmosis is the main one for desalination nowadays from seawater. Forward osmosis has found a number of applications as well in terms of industrial wastewater treatment, dairy, for instance, food, and so on. Membrane distillation is a very good technology to requirement because you have to heat up the water in that case. And the, I guess, classical pretreatment systems like NF, nanofiltration, UF, ultrafiltration, and MF, microfiltration, are used currently in a very routine manner across a number of separation processes, from wastewater to healthcare to also pretreatment of chemicals, for instance. But really, these technologies are the core ones which we can find for desalination purpose. And they are very good. But all of those only allow water or solvents to go through, in a sense. You will have some of the ions, some of the contaminants crossing at the same time, but they are more or less designed to allow for liquid permeation. And that's not always what you want. And the two other technologies which actually allow you to capture contaminants directly or to capture ions are electrodialysis and capacity ionization. And these two work obviously based on the charge of a specific material, which has to be conductive, in essence, and or at least which can be either charged directly or which can allow for transfer or adsorption of specific ions. And these will actually target those ions and not the water or not the solvent. So we have a bit of a dichotomy here between these two classes of membrane separation technologies. Today I'm going to talk about UF for the microplastics and electrodialysis for the cobalt and lithium recovery. Without getting into too much details there, obviously all of these technologies have a number of challenges and limitations, both from a process point of view, and some are inherent to the process, like fouling or scaling. You cannot do much about it. It has to happen because you concentrate something, and therefore you increase the stochastic chances to have specific adsorption and therefore strong adsorption between these contaminants and the membranes. And obviously, that membrane material will also have a number of limitations related to aging, related to wettability maybe, or related to that control of the homogeneity of a charge and pore size, as well as potential poisoning when you have active sites, like for electrodialysis. So I guess this table here just highlights to you that these technologies are, most of them are very well matured. They are commercial, but they're not perfect. And there are a number of applications that have been developed for things are well understood, but a number of emerging applications of with emerging contaminants, we need and we require better materials and actually combinatorial processes to tackle those. So what we have been doing for the last literally 8 or 9 years now is to develop catalytic or responsive membrane reactors, which allow you to treat selectively some contaminants in that solution, or to degrade them, or to selectively capture them from a complex birth or a complex mixture. And we have been looking at biocatalytic membrane reactor, electro, photo, phantom, and hybrid of those. The idea here is that we want to make sure if we have a like that blend of ions, lithium, cobalt, and others, like I will show today, that we can manage to force some of these one through at very, very high selectivity. Because recovering water is always valuable, but there are often more valuable compounds in water, or at least with the concept of circular economy I'm trying to prone, I believe we should pursue the objective of managing these effluents in a much smarter way to make sure that we can have a zero liquid discharge type processes, which means that we have an effluent coming in, we get the water out, and we get a number of products of value out of the brines which are being generated. And if we can achieve this, that will not only reduce the cost of desalination, it will also reduce the environmental impact of these brines, which are currently released either in oceans or in sedimentation and evaporation ponds. So it's trying to look at that those processes I just showed before in a much more circular way and in a much more environmentally friendly way. So without getting into details there, obviously we have been focusing on controlling materials properties in those contexts to limit fouling, to facilitate absorption, etc. And I have probably 6 or 7 examples I could show you, but we'll just be focusing on 2 today. The first one will be the development of conductive ion exchange membranes by electrodialysis and by tuning the properties of these membranes. And the second is on the surface modification of ultrafiltration membranes to control particulate matter, microplastics, fouling. So this work was really done on the battery spent effluent recovery by Anya, one of my postdocs. She's now back to Poland because of the COVID again, but she left us in August, and she has been working with us for about a year, a bit more than a year, on that project. And the objective of this project was to see if we could develop again a membrane-based technology to extract selectively some of these compounds in the battery spent effluent. Looking initially, because we have to make it economical, at lithium, which has a high value and a high, I guess. Sorry, there's a bit of background noise. Not sure if the mic is open. Yeah, thanks. So lithium has a great value and it's being mined and it's a finite compound. And you know that many battery technologies nowadays rely on these ones. I won't go in that detail, but it's really a major component of most of its rechargeable battery systems. And cobalt, which is not used in great quantities in those batteries, but it is of high cost. It's a few $1,000s per kilogram. And it is also extremely finite. So it's close to be one of these rare earth elements in those systems. So we have to make sure we don't waste it, and we must be able to recycle and put it back into the loop. And besides the membrane aspect, I will show you some work we have been doing on using mixed solvent extraction at the same time as membrane separation to facilitate the kinetics of diffusion and to facilitate the precipitation of these ions. So a bit of background there. This is for Australia, and I should actually get better numbers for globally or for Indonesia there. But if you look at the graph on the left-hand side, you can see these are projections for the amount of waste of lithium-ion batteries in Australia. And you have three scenarios: low, best, and high level. But regardless where we stand, we are around 2020 right now, or close to 2021, and we have, let's say, about 10,000 tons, a bit less on that, maybe 8,000 tons of waste per annum. But in 10 years' time, by 2030 or 2031, we'll have nearly quadrupled this, and it goes exponential afterwards. Of course, this will depend on the development of new technologies, especially solid state batteries, which are happening. But even if those technologies come in, the amount of batteries and the volumes and also their capacities will increase as well, which means they will require more lithium, more cobalt, and more of these finite resources. The cost of cobalt is on the order of $20,000 per ton at the moment as current. So it's quite valuable again. And in a battery like those, lithium ion, you can have between 0.1 to 1 to 8%, maximum in the spent solution there of cobalt. But if you look at those millions of tons of globally of batteries being used, this is still represents a large amount. Here it gives you an idea of a different share of compositions for the different main batteries, and you can see obviously that not all of those will include cobalt and so on, but there is quite a proportion of those where there is a need to make sure we do recover these elements. There's a link at the bottom there if you're interested. That's a very good blog on resource recovery and focused for that article on batteries. So I do recommend that you have a look here. And this article actually presents the different sources of components being used to develop the batteries. And you can see if we want to make it circular, what kind of looping are needed, what kind of looping are required right now to manage second life recovery and second life of these products. So I think it's really something we must strive for. This shows you a bit of an economy of scale there for recycling in China, and that's a fairly recent, again from the same blog paper, I think, which was published in July or August 2020. That gives you an idea of the total revenue expected, normalized by the energy cost there, and also what can be done in terms of gross margin and direct margin. And I think it's important to realize the breakdown of these components across the board, because the labor component is not the major one here, which means, and that's often a reason why recycling is not done, because most of these technologies currently made to recycle batteries, they don't require so much labor. And the major part of the labor is required for the dismantling of the battery, not really for the operation afterwards. So all the rest is really operational costs from a process point of view. And these can be leveraged and obviously can be reduced if you have an economy of scale happening. This graph is quite good, I think, because it shows you for different types of batteries, the composition with other metals. So like I said, I only focus on lithium and cobalt, but you can see that others like nickel, manganese, and are also there in large proportions, and they also have a value. So this value in terms of dollar per kilowatt hour really should be considered much more carefully to make sure we can collect those, extract those, and then put them back into the system. This is just a general one on the types of battery manufacturers for information, and recyclers as well. These are some are Australian, some are from the US, mostly in Germany. But there is a number of those, and China there. There's a number of those which are actually developing new technologies and new processes to get those things done. And so today, I just want to talk about that electrodialysis concept I introduced you to a bit earlier. And just to show you on the right-hand side, that's a typical stack of membranes dispatched in electrodialysis. So you have a number of membranes which have spacers between them in order to generate channels, okay? And once these membranes, which come in couples with an anion and a cation exchange membranes, are stacked, you put them between electrodes, and then you can apply a difference of voltage, which drives a current, electron diffusion across the membrane stack, and therefore diffusion of ions from one side of a membrane to the other, if the membrane, for instance, is able to allow for that hopping mechanism of diffusion. So here, if the dark membranes, dark red, are anion exchange membranes, the chloride can go through, but not the sodium. So we have those concentrated streams which occur here, while we deplete ions from that stream. So we alternate the concentrate and depleted channel across the stack. Okay, and I guess the idea here is that this has been demonstrated for desalination of groundwater, seawater, etc. But I wanted to understand how we could use that for lithium, cobalt, and other types of similar ions. One thing here, which is pretty obvious, is that these membranes have to be dense because we don't want to have water diffusion directly. We want to have ion diffusion, often with a shell of ions around them, but nevertheless, it has to be limited to those hydrogen ions. And therefore, if we look at the actual size of an ion in the solution, we have to take in consideration that shell around it. And interestingly, for cobalt and lithium, they have about the same size once you get in consideration the number of water molecules around them. So although cobalt is larger, it doesn't mean it will diffuse as readily as more slowly on lithium. And that's what I will demonstrate to you today. The second thing is that these chemistries of these membranes can be designed in order to be selective based on the valence on the ion. So you can look at membranes which are monovalent selective or divalent, etc. The more you push on the valence, the more difficulty you will have to drive ions through as well, because you will cross-link further your membrane. You will typically have less densities of those functional groups in the membrane, which allow for diffusion. So there is a trade-off between being very selective and obviously being highly permeable. So here, Anya really looked at two different strategies. On the left-hand side, she looked at the development of monovalent selective cation exchange membranes, because again, we only look at cation here because of the lithium and cobalt, okay? And she tried to understand how we could look at partial dehydration of these ions, depending on the cation exchange models used there. And in a sense, what we wanted to understand here is if we have pure water solutions or if we have a mixed solvent, how that will affect that hydration shell, okay? And how that will affect the diffusion potentially from the diluate to the concentrate side. The second strategy that she looked at is actually to develop those cobalt selective membranes by a specific polymerization process between PVC, which is a typical base to make unchanged membranes because it's quite solvent resistant and stable, and by actually looking at these compounds here, which are called 5-chloro-8-hydroxyquinoline, which have been shown because of these interaction between that OH and that tertiary amine functional group here, facilitate the encapsulation of cobalt ions. So that was published by another group recently, I think a couple of years ago now. And the idea was that they demonstrated it could be very selective for specific compounds. So first, one thing, like I mentioned at the start, we try to control the morphology of membranes, we try to control the surface area often, and also the density, because we want them to be very dense there. So Anya started from commercial membranes, Neocepta from Japan, and also made her membranes, trying to control the surface morphology there to facilitate diffusion and also to facilitate uptake. So most of the time you want to limit the surface area of a membrane because you want to limit fouling. And that's true for NF, RO, UF, MF type technologies. But in electrodialysis, you actually want to try to get more surface area to facilitate to have more diffusion rate in that case. And so she characterized those membranes quite extensively to understand, obviously, the differences in terms of chemistry. So that's FTIR on the left-hand side. I will not go into the details there, but that's common things here. And you can look at the paper if you're interested. And one of the nice things here that you can see on the right-hand side is the streaming potential, the charge of a membrane, in a sense, at different pH values. And what she managed to do is by looking at the different grafting procedure with these monomers here, either as a bulk when she polymerized them with a PVC, or just as a surface coating, she could actually tune quite readily the surface charge of those membranes compared to the commercial, membrane there. And this is important because to facilitate the diffusion of these cations, we want to have a membrane as negatively charged as we can, to some extent. One of the nice things here is that she managed to get what we call ion exchange capacity, which is actually the capacity of a membrane to hold for a specific uptake solution a number of ions. So here it's for cobalt, obviously. Nearly 60% more for this PVC bulk compared to the commercial membranes. That was already a very good sign that we could manage to attract more of these ions and obviously get them across the membrane by, I guess, basic diffusion, not even by applying any potential or current here. The contact angle is also important because you want to make sure that you have a decent diffusion across the material, but because we have very specific, I guess, morphologies, if it wets better, it's a really good point for us. It will help to have more interactions. So she made those modules and look at the diffusion of different solvents, pure water in some cases, or with a deep eutectic solvent, the DES solvent I will show you afterwards. But the concept was the same otherwise. And she developed some membrane which were lithium selective. I didn't show you the chemistry, but it was done, and others which were cobalt selective. Everything is normalized there in terms of y-axis on these diffusion rates. So you can see that PVC grafted gave us some of the best diffusion rates compared to the others. And that, in fact, the most interesting aspect was the selectivity, so the cobalt to lithium selectivity, and went from clearly nothing for the commercial monovalent membrane here, because it was actually not selective for cobalt, it was a bit more selective for lithium, to over 250 for this PVC, and even 26 there for the bulk ones. And that's an interesting thing because obviously this comes at the cost of the flux of, if you look at the things down there, at the flux of lithium compared to cobalt in a sense. So the interesting point there is that you can see that by controlling the surface properties of the materials, you can definitely improve by great extent the selectivity of these things. And here, if we really want to recover cobalt, such strategies can allow you to do so at a fairly cost-effective level, because the voltage across those stacks and the membranes were about 50 millimeter by 50 millimeters, so quite small, is quite limited. It's only 5 volts, okay? And in other processes, which are used industrially, they have to go to much higher voltages to generate these, to control the selectivity from the driving force, which we didn't have to do. The second thing she did, or she tried, is to look at these deep eutectic solvents. And yes, the idea here was to change the properties not only of the membranes anymore, but of the solution, to see if on the dilute side, on the concentrate side, if we could manage to alter the solubility of the ions and also alter their ability later in the track to precipitate selectively. And in a sense, she used a mixture of choline and urea, which is a known mixture actually using carbon capture, CO2 capture mostly, and try to understand the diffusion rates, the kinetics here for lithium and cobalt across the different systems at different concentrations. Okay. And we can see that actually we have an enhancement of diffusion when we have a larger concentration of that solvent, of that deep DE solvent in water. And we only have 0.25 weight% here, which is not much really, but we have nearly doubled already the diffusion rate. And it is something similar we got for the cobalt in that sense. I think it was actually more than that, nearly, roughly doubled. So if you look at these DES solvents as a subclass of ionic liquids at the end of the day, because people are looking a lot at selective extraction with ionic liquids, but they are very expensive and also can have some toxicity issues. But the DES are much more stable, much less toxic, and can allow us, like you can see here, for this calculation to actually capture much more of these ions compared to the reference water solution in essence. So she performed more tests with again the same membranes and with those mixtures of DES and water, and she managed to increase further, like you can see here, the PERM selectivity for the PVC grafted membranes. She nearly doubled them compared to what she had before. So generally speaking, even for the reference membrane, it looks like the impact of the solvent was beneficial to the diffusion, and that the solvent actually favored the desorption of the cobalt from the membrane, because we have nearly a factor 5 here, and here a factor 2. This is not true for the PVC bulk there. You can see we have less than we had before, because we had around 26. And that's likely related to the fact that we found that the PVC bulk modified, which had more monomer in there, had a great uptake of a DES solvent. So the diffusivity of a solvent was too good in the membrane here. And over here, they could not diffuse far or just at the interface. Here, the membrane captured the solvent, which prevented diffusion of the ions. This paper was submitted a few weeks ago, but if you have questions or are interested, we can further discuss. Quickly here, because I want to move on to the microplastics after this. There is obviously a number of things which have to be considered on the energy efficiency side. So what we try to understand here is how our different membrane systems we have developed there with DES, so that's the gray stuff, or without, could be comparing to the CIMS commercial membranes there. And we can see that for most of those, we had, especially for the in terms of gram per joule, gram of ions collected per joule, we have quite a strong increase. And actually, if we look at the DES concept, the bulk led us to some improvements, and but otherwise here, the energy consumption was similar, I guess, compared to the DES for the membranes, which were just in terms of watt per gram of salt used. So we still have to refine this. We still have to tune further the chemistry there and potentially play with the solvents to make sure we can prudentially limit the penetration in those bulk membranes to try to, again, limit that energy consumption altogether. And this graph actually relates to that directly. That's actually looking now at constant currents as opposed to constant voltage, but we had similar permeation and similar behaviors. So I won't go into this, but in a sense, those PVC grafted with the monomer grafted on the surface was always better compared to the others. And she made similar calculations there. So in conclusion for this first part, what I want to say is that there is a lot of work to be done on the material side to further improve these concepts, and that if we want to be selective, if we want to have highly efficient systems, we need to rethink the way we do things, because often people want to be fast and have great selectivity, and that's not always possible. Now we are touching limits of thermodynamics, and also if you have fast flux of different components, it often leads to more fouling, to more detrimental effects on your materials and on your membranes. So I think we have to accept the fact that we need to be slow for some things, but we need to be able to do it extremely selectively. And if we do so, like I did show you for some of these examples, the economics follow. So there is great potential to pursue that circular economy aspect by not trying to be always, by being efficient, but in the sense as we need to be selective to get a product nearly pure out of a single process. So I would like to thank Dikin and the ARC for funding and a number of our partners. I will not stop there, so we'll move straight away to the next talk. But if you have questions on that first one, I'm happy to take them before I move to the microplastics.
Okay, thank you very much, Ludo, for your nice talk about the electrodialysis for lithium or battery spent waste recovery. I think we have one question here from Dr. Emma Safitri, uh, one of my colleagues. How is the possibility of using biomass, for example, chitosan or cellulose as composite membrane in the commercial application, considering their mechanical weakness? Do you have any idea about that? Thank you.
Yeah, no, thanks. That's a good question. There are a number of groups looking at using natural products or biopolymers to make membranes. So that's fine. This is not a big deal. Um, there are constraints to that, and I will come to it in a sec. But I think the mechanical strength of a membranes, because membranes are always tested or applied in compression, not in tensile. Okay, so people often report tensile strengths of membrane, but that doesn't really make sense. Okay, so membranes are always sandwiched; they are compressed by the different streams, and whatever process you have a pressure difference between the two. So unless the membrane is really not cohesive at all, the material is not cohesive at all and falls apart under very mild compressive pressures, that's not common. Using biomaterials is okay. So using biomass, it has been used a lot to make activity carbons or activity carbon-based membranes is fine, okay? Even I had a project recently where we used bacterial nanocellulose to make membranes, okay? That directly from mushroom and bacteria growth, okay? So they grow those networks of nanofibers, and we made membranes, UF membranes out of those in one go. So that's fine. That's really something which is happening. I guess the question is always, some of these membranes are very cheap. So not electrodialysis, but NF, UF, and so on, they are quite cheap. So if you want to compete with those, whatever process is put in place with those biopolymers has to be cost effective, the process and on the material sourcing.
Okay, thank you very much, Ludo. I think we still have only that question for you, and then you can continue to your next presentation. Thank you.
Yeah, all right. So I wanted to show you a bit of work we are doing on the. Can you see? Sorry, can you see my second slide? Can you see the second set of slides?
Yes.
Okay.
Yes.
Good. So I just wanted to touch base on that because that's a big challenge here, and we have 3 projects now work on microplastics, and I know in a number of countries it's emerging. People are realizing the risk of having too much plastic pollution in ocean, in river, and so on. So and I think Putu mentioned that some of you guys were working in that space as well when we talked last year. So I just wanted to show you what we have been doing on I guess a bit of extraction, but mostly on the impact of microplastics, both particles and fibers, on the performance of membranes which are used in wastewater treatment plant. And there is hardly anything here at the moment, like hardly any data. And that's a bit worrying because when we look at the levels of pollutions, we talk of a few million tons per year of plastics released in the ocean. I mean, this is huge, okay? And we don't understand what's happening. We understand it's toxic to fish. We understand it's toxic to a number of yes biomes, but we don't really know how it's affecting us. Okay, and at the same time, we don't really know how these are sorry how these would be behaving, like I will show you today in okay, in wastewater treatment plant or desalination plants. So this work was really done by one of my students, Marie Enfrin, who is finishing her PhD now, and with a collaboration from Surrey University, Dr. Julie, who put to my know because she was at Melbourne a while back when he was in Australia. So it's really Marie's work today, and again looking at these fouling on UF membranes per se. So without getting into the details there, you can imagine people have reported the occurrence and the quantity of microplastics into different streams, looking at beer, looking at salt, looking at fish, water bottle. And you can see that actually water bottle is not safe. Yeah? You have much more microplastics reported in water bottles compared to tap water. So you can have other issues with tap water. I'm not arguing this, but in terms of microplastic occurrence and potential threat from that, we have to rethink what we do. The textiles are also a massive source of microplastic release, and a single wash can release up to nearly 1 million microplastics fibers. That's huge again. And that's, like I will show you today, that's actually just considering what people are able to see. because detection of microplastic is really the main challenge right now, because people can only see what is down to a few micron or tenths of micron level. Whatever is nano is not reported. And yeah, a few numbers there, but people have shown that we ingest on a daily, we have about 20 microplastics per gram of body mass, okay? And we ingest a few hundreds of microplastics, saying per day or per minute right now. But what interested us really in that project is to understand if you have an effluent coming with some plastics, okay, nano, micro, fibers or not, into a wastewater treatment plant, would have been estimated the amount that is being released there per day for different sizes of plants. And because membranes are a real part of these systems, and you know that fouling is a big issue there, we wanted to understand how these might affect those membranes. And is it likely that they would breach those membranes or not? And if they do, how would they interact with them? Would they not do anything at all? Would they increase fouling, or would they damage the membranes, for instance? So we looked at obviously a number of things here, looking at one single type of membranes, in fact, but we looked at how we can modify them to control the surface charge again. So, you know, it's always my thing. To understand if fouling occurred, what we could expect. But typically we expect lower flux and higher rejection, that's a typical thing, but also a shorter lifespan of the membranes. And if we have to clean them, that further reduces the membrane lifespan. So we go into that vicious cycle of keeping performance high up in terms of flux, but losing in terms of material integrity and so on. And obviously increasing operating cost at the same time. So we wanted to understand if we change the shape, the size, the charge, the polarity of the particles there, how it would affect, based on the membrane properties, those patterns. And I will show you two things today. The first one is how we synthesized short nanofibers. And so we used electrospinning for that to make aligned fibers, or fairly aligned fibers. And their diameter was around 200 nanometer in length for a length of, give or take, I think 5 microns. Okay. And after a specific set of treatments, we looked at how we could isolate them to then use them as a feedstock for our filtration processes. And that's, in a sense, how she made it. I won't go into the details there, but she spun them, cut them, use a material to freeze them, and then cut them down to microtome to get very thin slices of those fibers. And the video is very noisy, so we'll not put it there. And obviously, we have to characterize those guys to understand if we could remove that material use of a freezing, and also understand the concentration and the levels we had in solutions. Okay. So the second thing we use is so the first one we synthesize ourselves. Here, the second material we use is actually microplastics from a face scrub, which is not for sale anymore. But when Mary started 4 years back a PhD, you could buy it off the shelf in the UK. But literally that came from, I think, one of the major supermarket brand in the UK, and she bought 10 of them and had enough for her PhD. But in those guys, they were up to 2.5% of plastics. So, you know, it's a massive amount when you think of the tons or megatons we have been, you know, selling to people over time. And some of the microplastics, we found their sizes range from 10 nanometer to 700. And I would really be wondering what happens when you are below 100 in terms of uptake by cells, by the skin, and so on. So, I mean, this is a health issue here. And the membranes we use were commercial polysulfone, okay, classical UF-based with a pore size around 30 nanometer, let's say. So we obviously characterize them to what they were. And we use a cross-flow system like this one to do the filtration. So the first thing I want to show you is what happens when we filter those microplastics. So the top line here is just pure water, no plastic, filtration for nearly, I think, 48 hours, so 2 days continuously. And looking at the surface of membrane after 48 hours on the top right corner. It's not damaged, it's not fouled, you can still see the pores there, it's nice, okay, no issue. When you add microplastics at 10 milligram per liter, this is what you see after 48 hours. The membrane is completely clogged. You cannot even discriminate the plastic particles together, because although here we had a good distribution to see them, they are all mixed and we have lots of variation in size. So it's a very classical cake layer like we would expect from groundwater or wastewater treatment purpose. And the flux went down extensively by nearly 50% in 48 hours. Without cleaning here, it's just basic step. So it still showed us, okay, first, yeah, there is an issue. They accumulate quite badly. The pressure differences here were quite low. We are around, I think, 1 or 1.5 bars, so not high strength, membrane pressure, and the impact at those concentrations, which could be arguable, but yet is quite dramatic. But how do we go from seeing that on the surface to understanding how much particles are on the surface or are still in the liquid, in the effluent after crossing the membrane? So we use the technology called the nanoparticle tracking analyzer, NTA, which is fairly recent. The first units were commercialized about 10 years ago. And it works a bit like DLS, except that the algorithm is quite different. And there is a laser scanning a microfluidic chip, which we have a cross-section here, and it will scatter light around those particles. And the scattered rings of light around the particles will allow you to determine, with the right algorithm, the particle size distribution. The software is pretty smart here because it will take a video of whatever goes through that microfluidic chips as the particles circulate, and it will therefore track each particle individually to make sure it's not counting them several times. Okay, and that's important because that allows us to get size and number distributions of the same sample. Okay. The main challenge here is that it has to be fairly concentrated. So we need at least 10 to the 6 particles per milliliter to work. Okay, so that's a challenge. And the second challenge is that this is good for nanoparticles up to a micron. That doesn't work for anything larger. But like I said at the start, most of the work to date has been done on microparticles, not on nanoparticles. So by doing so here, and because of a range of particles we saw, it was still relevant for our study. So when Mary prepared the fibers or the particles, she made sure that she had nothing larger in terms of particle size beyond the micron initially by having a prefiltration step to only take those nanoplastics in consideration. So just a quick video here so that you can see the particle moving in the microfluidic channel. And if you look on the right-hand side, you can see the track of each particle. That's a snapshot there. So the software knows where they are. If they overlap at some point, it doesn't count them twice. And therefore, you can see those scattering rings around them here, which will correlate back to the size of those particles. So what are the interactions we can expect between those particles and the membranes? And I'm conscious of time, so I will go through this quickly. Mary calculated the amount of particles being adsorbed on the membranes and related back to the different pore blockage and Kekulé formation mechanisms. And there is 3 of them, intermediate, complete, and Kekulé. If you have questions on those, I can take them further, but she has been doing some modeling to understand for each part of the curves where we're standing here. And in essence, what we found is that we had a quite large contribution of a complete pore blockage, meaning some small particles were getting inside the membranes and blocking the pores completely. And obviously, like we could see from the SEM, we had a Kekulé formation. But the intermediate pore blockage one was not found to be significant in terms of behavior there. Those solutions were quite basic, quite simple, just microplastics in water. And now we are doing tests where we complexify by adding surfactant, by adding other things there to see how we can come closer to a real wastewater. The second thing she's done is to look at the nanofibers. And like I mentioned at the start, you can have a few 100,000 to a few million fibers being released per wash. That depends on the capacity of the washing machine and many conditions, but which will correspond to a mass of nanofibers released between 2 and 10 milligrams, depending on the reports, per liter. Okay? So it's quite decent in terms of concentration here. So the challenge we had here, we could see the fibers, but we could not use the NTA because of a scattering issue to determine them. So we use actually just basically the turbidity of a solution to calculate that, and with UV spectrophotometry. And that allowed us to get an idea of the transmittance at different concentrations to therefore calibrate our system. So it was more indirect, and we could not get size and concentration at the same time. Because the fiber length and diameter were very controlled, we had very little variation there. So it was not as important for the fibers. In order to control these interactions and again limit fouling, what Mary has done here is to use plasma polymerization with different monomer, but I'm only reporting for acrylic acid here, to modify the surface and in a sense to make the membrane a bit more hydrophilic, a bit more wettable, which often makes it easier to clean. And she characterized them. She could see that we could control, based on the polymerization time, in a sense, those bands, IR bands there corresponding to the acrylic acid, in order to increase the thickness, in a sense, of the material. And that's just SEMs there to show you how it does change. So we densify a bit the membranes as we add the layer, but again, the purpose is to control the charge, so we have to compromise somehow. And interestingly, if you look at those data, you have the same flux of the same graph I showed you before of normalized flux over time for 48 hours. We had similar decay, but we have much less decay for the membranes which were polymerized, for instance, here for 3 and 5 minutes, which means we had less interactions between the particles here and the membranes. And again, when she calculated the amount of particle absorbed after 48 hours up to here, we had much less particle absorbed on the membrane compared to so about 10 to 12% compared to 30% for the plasma modified membranes. So going in the right direction, but this obviously comes at the expense of the absolute flux of the membranes, okay? Because we are reducing altogether by between 20 and 40% the flux, pure water flux, because of the plasma layer polymerized. But like I said, I think we have to move back from making always things faster, and we have to agree on sometimes on making things a bit slower, but more efficient. That's my motto here. And after cleaning, we could recover. So it was a basic water cleaning here. She's done, and she could recover quite a bit of particles from the membranes, close to 90% in a sense. And for the 1 minute, not so much, which tells us we have probably a patchy coating. You know, the PSF is still present. It's not fully covered. Therefore, it didn't release everything. But at 3 and 5 minutes, the release was very good. Just to show you the membranes after the 48 hours of filtration, there is no difference. Okay, you cannot see a difference there. They are all fouled about the same, but obviously the difference might be in the thickness of those coatings, which we cannot determine here, and also on the adhesion, how strongly adhere these are. That's a different issue. She characterized the membranes in terms of wettability, roughness, and swimming potential. I'm not going to go into that, but you can see that we had a massive impact, obviously, of a coating on these things. And at the end of the day, the outcomes for her study and what she has been working on so far is that we can see we have a very strong dependence on the type of particles and also on the impact of their shape and surface chemistry on the fouling behaviors. And therefore, because we cannot control in real wastewater conditions what these fibers are, all these particles, they come as they are. You know, we need to modify the membranes to make sure we are less sensitive to these conditions. We have one project starting. It was delayed because of COVID, but hopefully by the end of the year or early next year with real wastewater systems in Deakin. And now we are also looking more at the toxicity impact, looking at how these particles will affect fish, will affect mice and stuff like this, because we want to make that relationship onto. The question there is, if we generate concentrates of microplastics from the wastewater systems, is it going to be an issue as well? Are we going to release something toxic back to the river, so back to the so do we need to capture everything before it is released? So that's it for me today. If you have questions on this talk, I'll be happy to take them, and I'm nearly on time. So I hope we have time for sort of healthy discussion afterwards.
All right. Thank you very much, Ludo, for your very nice presentation about microplastic. We have some question here. First question is from Dr. Lani Sapei. She has two questions. The first one is, what is the molecular weight distribution of microplastic? How you determine whether RO, UF, or MF are suitable? And which one is the most used? That's the first question. Yes.
So microplastics are not defined by molecular weight per se, because they are very large. I mean, monomer, polymer per se can be, but most what we use here for the microplastic were all PET, so PET particles and PET fibers. And I think for the molecular weight of the polymer we used to make the fibers was around, I could be wrong, 1.5 million, but I could be wrong there, so we'll have to check that. But the idea is that it's more important to look at them as a particulate matter as opposed to what molecular weight they have, because they are literally physical particles per se, and also we cannot determine whatever goes down to less than 10 nanometer at this point. It's very hard to see them or to really identify them from these solutions. So that's my first answer. Now, right now, there is nothing done to remediate them, literally. And we have talked to a number of water authorities in Australia, and they are all very interested, but no one wants their waters to be tested because they know there's going to be some plastics in there anyway. So the project we have, and I can't disclose with whom in Australia, with one of those who were more keen to try. Obviously, they understand they have maybe some industries close to their, I guess, intake of wastewater, and that these industries are likely to release some microplastics, at least to some level, and therefore they want to understand if the operation they see in their plant are directly related to potential presence of these components in the influx water. Okay, so I guess right now, in terms of which technology will be more relevant, that's a very good point. And because of the size, MF or UF are likely the most interesting ones to me, okay, in terms of pretreatment. However, if we want to capture them, they won't work because the cake layer is too bad. Yeah. So we need to look at selective adsorption of microplastics in that case, with maybe carbon-based adsorbents or like we discussed before, biosource-based materials for as a capture materials, and these would have more potential. There's maybe 3 papers I've found so far on adsorption on microplastic, and I think that was one of the projects we talked with Putu last year actually to see if we can develop something together when I was meant to come over. So I think to me, anything related to remediation should go in the direction of capture, okay, by adsorption. And sorry, and the other thing is that besides this, depolymerization of that stuff, because what you do with them once you have them, and for large wastewater treatment plant, that might be, a few, maybe ton per year and so on, but at the country level, that can be very large. So what do we do with those? So I think we should also think of how can we put them back into the system? So we have these PET, these polyethylene, polystyrene, whatever. How can we depolymerize them, like we discussed initially, to then put them back into that loop, to make something out of those and not having to bury them or burn them, which would be a bit sad.
Okay, thank you. And the second question from Dr. Lani is, does fouling always occur in all types of membrane material used?
Yes, it always, and you can't do anything about it. Fouling is flux driven. People often think it's pressure driven, but that's wrong. It's flux driven. The more flux you have, the faster you concentrate on the surface, so the more fouling you have. And fouling occurs mostly in water, liquids, let's say water, but it also occurs in gas phase. Okay, you can have actually gas fouling of membranes, which inhibit diffusion of other molecules. So if you look at natural gas separation, CO2, CH4, both gas can always diffuse in the membrane, but one is more selective on principle across. And what the lack of selectivity is often, or the lack of the decrease in performance over time, are related to incorporation of some of the other gaseous molecules into the top layer of the membrane, which is the same thing as fouling. Same for hydrogen as well. With metal membranes, you also have the same type of behaviors there, with carbon components diffusing into the top layer only and fouling or scaling, if you want, the surface. So yes, it's always happening. And all we can do is to try to facilitate cleaning. I guess we cannot prevent it, so we have to make sure we have gentle and easy cleaning steps where the material is either resistant or is not being damaged by those.
Okay, thank you, Ludo. And the next question is from Dr. Emma Savitri. What are the advantages, especially in economic point of view, of using membrane technology compared to other technologies to handle the microplastic problems? Thank you.
Yeah, that's a good one. This one on the economics, I don't know. Okay, I think right now, before we try to, we should try to understand how we can capture them. And again, like I said at the start, I don't think the membranes are necessarily the solution to capture them. There are better ways. But if these effluents reaching wastewater treatment plants or desalination plants contain microplastics, we must know it because the impact is real and is strong. So I think the purpose for us right now is not so much to look at the economics of the capture or reprocessing per se, I guess. It's more to understand how they will impact those processes already in place, like MBR, membrane bioreactors, like those UF, MF, potentially the flocculation step in those wastewater treatment processes, and see if they might have a positive impact sometimes, who knows, or they might have a very negative impact as well. So there is a lot of work to be done to understand how they are impacting things right now, to then go into further, I guess, more advanced directions in terms of where the research should head off.
Okay, thank you, Ludo. And I would like to inform you, actually, we just started like a collaboration with Nanyang Technological University in Singapore. We would like to conduct research on microplastic as well using a membrane. And what do you think about MBR? I mean, compared to UF, MF, or RO? Because I read in some reviews paper that they mentioned that MBR is better than RO, UF, or MF to treat microplastic. Thank you.
So I have another student working on MBR right now. I mean, microplastics on MBR in Australia. So my second PhD on that topic is working on that. And I think you can. I mean, I'm not sure. I would not compare RO and MBR. I think they have very different purpose. RO is really for desalination. That's it. Okay. MBR is for the treatment of low molecular weight organic compounds. So they are not used for the same thing. And you would never have them, as far as I know, unless you have a very specific effluent in the same location or in the same plant. But I think if you compare UF to MBR, obviously that's good. And I think there it depends again on the composition of your wastewater. So if you look at desalination, MBR doesn't really make sense. I have not seen many or any applications of MBR to help in the pretreatment of very saline waters, because the bacteria, they don't like it, or the algae don't like it, so they will die likely. It's because it's very hard to keep them alive. But if you look at the municipal wastewater, that's where most of it is done, right now, and there's a great potential here, especially because you have fibers going into that wastewater at the same time, at least from the washing, and maybe many other things there. So that's why I think doing the MBR aspect is important. And most MBRs, are either UF or sometimes MF, but mostly UF based. That's why actually we started with that UF project, and now we're moving to UF MBR to have a continuity, because we understand how the fouling occurs, and now we want to try to see how the relationship between bacteria and membrane and microplastic goes. So yeah, I'll be happy to discuss further if you guys are interested in that aspect, and see if we can put something together.
Yes, of course. Because we just started collaboration, maybe you want to work with us as well. I will talk with my colleagues here about the possibility to involve you in the project. Probably, is it possible?
Yeah, sure. Like I said, that's what we spoke today. So just try to see if we can find common interest and to develop something together. And again, I hope I can come next year to further do this. In Abu Dhabi, I've been looking at funding in that space. I guess I have seen nothing yet on the microplastics per se. There is a lot of things on PFAS and other types of micropollutants, but not microplastics. It's not something which is under their radar, I guess, yet. But at the same time, when I talked to water authorities a couple of weeks ago, they said they would be interested to have a look at this. So I think it's emerging everywhere. Like in Singapore, water is massive there. In UAE, there is like no water at all. Everything is desalinated. So it's areas where we need to do something for sure.
Okay, thank you, Ludo.
Thanks a lot.
Is there any question maybe from the students? You can raise your hand here.
Don't be scared. I can't bite you today because I'm not on site. So.
No question? Okay. I think we already passed 1 hour for our session today. So once again, thank you very much, Ludo, for your great talk today. And it is very glad to have you here, even though through online, not offline. Unfortunately, this year we cannot see each other offline in Surabaya, because you already booked your ticket and your accommodation in Surabaya, but because of COVID-19, you couldn't come to Surabaya and Bali this year. I hope next year or in the on the future you can come to our country, because you never come to Indonesia or Bali, right?
No. That's on my list.
Okay.
Yeah.
All right. So I think the session today is very important for the students and also for our lecturer here to know about your research work in Deakin University and also in Abu Dhabi. I hope you enjoy your stay there in Abu Dhabi. So is that your permanent position now?
Yeah. So
Okay.
it's a tenure track. So
Okay.
so look, I have not really started yet. So I think it looks good. It looks promising, and
All
and I
right.
want to give it a good shot. There are lots of opportunities in terms of funding, more than in Australia, in fact, right now. Australia
Okay.
is a bit difficult. But yeah, I think for the next 5 years at least, I'm gonna be there for sure. So yeah.
Maybe some of our students want to continue their study. Maybe he or she can apply for a
Yep.
research opportunity in your school or your research group in the future. Is it possible,
Yep.
right?
Yeah, absolutely. Master and PhDs are available. There are scholarships provided by the university. And if you're interested, just contact me. My email was on the slide there. And there are also a number of project-related, research projects, research things which come up for master and PhD. So absolutely, contact us
Okay.
and we'll be happy to. And if it's not with me, I can diffuse your CV to colleagues. If your
Right.
interest is different, that's no issue.
Okay. Okay. Thank you very much, Ludo.
Much. Thanks all. Thanks for
Yeah. Okay. As an information, Ludo is very active on Facebook. So if you have a Facebook account, maybe you can contact him through Facebook Messenger or his Facebook account.
or
Uh,
LinkedIn. Yeah.
yeah. Okay. Thank you very much, Ludo. Enjoy your stay in Abu
Thank
Dhabi
you so
and
much. Thanks.
good luck there. And see you in the near future.
Yep, let's keep in touch. Thanks a lot. I really appreciate the opportunity to talk
Okay.
today.
Thank you.
It was
Thank you
really
very
nice.
much.
Thank you.
Thank you very much,
Thank
Ludo.
you.
See
Thanks
you.
all. Bye bye. See you.
Bye bye.
Bye, Eddie. See you.
Untuk mahasiswa peserta TRK 1 mungkin bisa stay, dan untuk mahasiswa lain dan Bapak Ibu dosen mungkin bisa leave meeting. Ada Bu Natalia, Bu Emma, Pak Edi, Bu
Thank you,
Lani.
Pak Putu.
Ya, sama-sama Pak Edi. Sukses di sana Pak Edi.
Terima kasih.
Tunggu segera Pak Edi.
Ya.
Untuk yang mahasiswa peserta TRK 1, kita lanjut sebentar ya. Apa namanya? Mungkin kita coba lihat latihan soal ya. Ini apakah masih ada peserta di luar TRK 1? Kalau mau ikut juga nggak apa-apa sih. Baik, saya izin share screen ya. Ya balas WA-nya si Ludo dulu ya. Dia soalnya nawari student exchange ke sana. Atau mungkin bisa ada peluang untuk student kita yang pergi ke sana nanti ya. Coba lihat, sorry. Halo, bisa dengar suara saya?
Bisa, Pak.
Bisa, Pak.
Oke, mudah-mudahan belum capek ya. Baik, kita coba lihat contoh soal yang ada di textbook Pogler ya. Jadi minggu lalu itu kita membahas sedikit tentang susunan CSTR seri di mana ukuran volumenya berbeda ya. Kalau ukuran volume CSTR-nya berbeda, maka nanti ada dua problem ya, dua permasalahan. Yang pertama adalah bagaimana menentukan susunan reaktor kalau misalkan konversi akhirnya diketahui. Kemudian permasalahan kedua adalah bagaimana menentukan konversi akhir yang diinginkan kalau misalkan susunan reaktor CSTR-nya sudah ditentukan. Ya. Itu semua sudah kita pelajari minggu lalu, termasuk juga saya sudah memberikan contoh soalnya. Ya. Nah, kemudian di akhir minggu lalu juga saya sedikit menjelaskan tentang optimasi dari susunan reaktor susunan multiple reaktor atau susunan reaktor yang jumlah reaktornya lebih dari satu ya. Jadi minggu lalu kita sudah membahas bahwa kalau order reaksinya itu atau kurva laju reaksinya adalah kurva laju reaksi yang cekung ya. Kalau cekung itu artinya kita berusaha mempertahankan konsentrasi reaktan di dalam reaktor sebesar mungkin ya. Jadi kalau kurva laju reaksinya itu cekung ya atau monoton naik ya, maka sebaiknya kita mempertahankan konsentrasi reaktannya sebesar mungkin. Jadi kalau ada susunan reaktor misalkan PFR dengan CSTR, maka kalau kurva laju reaksinya itu cekung atau monoton naik ke atas, tetapi cekung, ya, maka kita menyusun PFR terlebih dahulu diikuti dengan CSTR. Nah, begitu juga sebaliknya kalau kurva laju reaksinya itu adalah kurva laju reaksi yang cembung, ya, maka kita sebaiknya mempertahankan konsentrasi reaktan di dalam reaktor sekecil mungkin. Jadi contohnya misalkan kalau kurva laju reaksinya cembung ya, saya kebalik-balik cekung sama cembung ya, yang cembung gitu ya, maka yang memberikan volume terkecil itu adalah kalau kita menggunakan reaktor CSTR terlebih dahulu. Jadi artinya kalau kita menggunakan CSTR maka konsentrasi reaktan di dalam reaktor itu kita pertahankan sekecil mungkin. Nah, sekarang coba kita lihat contoh soal yang ada di Pogler ya. Ini pernah saya keluarkan juga pada saat ujian akhir 2 tahun yang lalu ya. Jadi kalau kita misalkan punya data di sini ada konversi dan laju reaksi X dan min RA, ya. Kemudian diketahui suhu dan tekanan. Kemudian reaktan A itu masuk ke dalam reaktor, diikuti dengan adanya inert dengan perbandingan yang ekimolar, ya. Jadi kalau dia ekimolar, artinya fraksi mol dari komponen A dan komponen inert itu sama-sama 50% atau 0,5. Kemudian diketahui laju alir volumetrik total ke dalam reaktor adalah sebesar 6 liter per second. Pertanyaan pertama, hitunglah volume reaktor CSTR yang dibutuhkan untuk mencapai konversi sebesar 60%. Kemudian yang kedua adalah hitunglah volume reaktor CSTR untuk mencapai konversi 80%. Jadi kalau yang pertama itu kalau konversinya 60% atau 80%, maka yang kita buat adalah kita tambahkan satu kolom, ya. Jadi seperti yang sudah Anda ketahui bahwa dari persamaan desain reaktor CSTR, persamaan desainnya adalah V dibagi FA0 sama dengan X dibagi min RA, gitu ya. Di mana luasan persegi panjang pada kurva 1 per min RA versus XA itu merupakan volume dibagi dengan laju alir molar atau V dibagi FA0. Jadi di sini yang kita lakukan adalah kita buat satu tambahan kolom, ya, kita hitung 1 per min RA, sehingga ini kalau kita plot, ya, itu akan menghasilkan kurva seperti ini. Nah, jadi kalau pertanyaannya adalah hitunglah volume reaktor CSTR untuk mencapai 60% dan 80%, maka untuk yang 60% berarti ini ya, 0,6 ya, dikurangi 0, kemudian dikali pada 0,6 itu sumbu Y-nya adalah kebetulan di sini 400 ya. Jadi 0,6 kali 400. Ini ya. Kemudian kalau yang 80% konversinya itu artinya di sini ya 0,8 dikalikan 800. Ini ya. Ini contohnya misalkan yang 80%, kalau dia CSTR, maka volumenya bisa kita hitung dengan menghitung luasan persegi panjang, yaitu 0,8 dikali 800. Nah, kemudian untuk menghitung volume, karena ini luas persegi panjang ini adalah sama dengan V dibagi FA0, ya. Jadi ini ya, V dibagi FA0, ini merupakan luasan persegi panjang, karena sumbu X-nya adalah X, kemudian sumbu Y-nya adalah 1 per min RA, jadi 1 per min RA dikali X, itu merupakan luasan persegi panjang. Maka di sini untuk menghitung volume, kita harus menghitung laju alir molar senyawa A pada saat awal masuk ke dalam reaktor. Ya. Nah, itu kita hitung dengan menggunakan rumus CA0 dikali V0. Ya. Jadi CA0 kali V0. Di mana CA0 ini adalah sama dengan, atau kita asumsikan dia mengikuti gas ideal, persamaan gas ideal, maka CA0-nya kita hitung dari persamaan ini ya. Ini. Jadi P dibagi R kali T itu adalah konsentrasi. Karena konsentrasi itu adalah jumlah mol dibagi dengan volume. Ya, di mana untuk menghitung CA0 ya, itu sama dengan PA0 kali R kali T0 ya, atau tekanan parsial A pada saat awal dibagi dengan konstanta gas ideal dikalikan dengan suhu ya. Kemudian tekanan parsial A itu adalah sama dengan tekanan total dikalikan dengan fraksi mol senyawa A ya, yaitu sama dengan 0,5. Ya, tekanan totalnya adalah 10 atm, maka tekanan parsialnya adalah sama dengan 5 atm, ya, dibagi dengan R kali T0 dikali dengan V0. Sehingga nanti Anda dapatkan nilai dari laju alir molar senyawa A pada saat awal, atau kita sebut sebagai FA0, ya. Jadi itu yang pertama, yang CSTR. Kemudian yang kedua, hitunglah volume reaktor PFR yang dibutuhkan untuk mencapai konversi sebesar 80%. Jadi untuk menghitung reaktor PFR, maka untuk reaktor PFR, kalau kita menginginkan konversinya 80%, sesuai dengan persamaan desain untuk PFR, maka volume dibagi dengan FA0 untuk PFR itu sama dengan luas area di bawah kurva, ya. Luas area di bawah kurva. Nah, kalau menghitung luas area di bawah kurva, maka kita di sini bisa menggunakan persamaan atau metode Simpson untuk menghitung luas area di bawah kurva. Jadi untuk metode Simpson-nya kita menggunakan metode Simpson untuk 5 poin. Karena di sini ada 5 poin, 1, 2, 3, 4, dan 5. Jadi kita gunakan Simpson 5 poin, ya. Di mana delta X-nya ini adalah masing-masing sama dengan 0,2. Ya, jadi delta X-nya adalah 0,2. Di delta X 0,2, maka di sini kita gunakan rumus. Jadi 1 per min RA pada saat X sama dengan 0. Jadi 1 per min RA pada saat X sama dengan 0, ini ya, 189. Kemudian plus 4 dikalikan 1 per min RA pada saat X sama dengan 0,2, ya. Jadi 4 kali 200. Kemudian 2 kali 1 per min RA pada saat X sama dengan 0,4, itu adalah 2 kali 250, yang ini adalah 4 kali 1 per min RA pada X sama dengan 0,6, yaitu 4 kali 400. Kemudian 1 per min RA pada X sama dengan 0,8, itu adalah 800. Jadi kita lihat di sini bahwa volume dari reaktor PFR itu ketemunya adalah 225 liter, sementara yang CSTR itu ketemunya 554,9 liter, ya. Jadi artinya kalau kurva laju reaksinya itu adalah kurva laju reaksi yang cekung seperti ini cekung ya, yang monoton naik tetapi cekung seperti ini, maka untuk membandingkan volume reaktor yang kita butuhkan, maka untuk bentuk kurva yang cekung seperti ini, kita sebaiknya memilih reaktor PFR, ya, atau bisa dikatakan kita memilih reaktor supaya konsentrasi reaktan di dalam reaktor itu sebesar mungkin, ya, karena pada PFR kan bentuk reaktornya adalah berupa suatu pipa, sehingga selama reaktan itu bergerak dari ujung awal masuk ke ujung keluar dari reaktor, ini penurunan konsentrasinya relatif lebih kecil dibandingkan dengan reaktor CSTR. Jadi itu maksud dari kesimpulan kita minggu lalu, bahwa kalau kurva laju reaksinya itu adalah kurva laju reaksi yang cekung, maka sebaiknya kita mempertahankan konsentrasi reaktan di dalam reaktor sebesar mungkin, atau kalau kita dihadapkan pada pilihan antara PFR dengan CSTR, maka sebaiknya kita memilih reaktor PFR. Atau kalau misalkan reaktornya ada 3 jenis, ya, 1 PFR, 1 reaktor CSTR kecil, kemudian yang satunya adalah reaktor CSTR yang besar, maka yang kita lakukan adalah kita pasang yang PFR di urutan pertama, kemudian CSTR kecil di urutan kedua, kemudian paling akhir adalah CSTR yang ukurannya besar. Dan pertanyaan ketiga, hitunglah total volume 2 reaktor CSTR yang disusun seri jika diinginkan konversi keluar di reaktor pertama sebesar 40% dan konversi di reaktor kedua sebesar 80%. Jadi kurang lebih skemanya seperti ini, ya. Jadi kita menggunakan 2 reaktor CSTR. Reaktor yang pertama itu konversi keluar dari reaktor adalah 40% atau X sama dengan 0,4. Kemudian di reaktor kedua konversi keluarnya adalah 80%, atau X sama dengan 0,8. Jadi jangan sampai keliru di sini menggambarkan untuk yang reaktor kedua, ya. Jadi ini 0,8 kita tarik ke atas, ya. Kemudian ini kita tarik ke kiri sampai konversi mencapai 40% di sini. Kemudian kita buat persegi panjang. Nah, ini persegi panjang ini luasnya adalah sama dengan V dibagi etanol untuk reaktor yang kedua. Jadi untuk reaktor yang pertama itu adalah berarti di sini luas persegi panjangnya adalah 0,4 dikali 250 ya. Kemudian untuk yang reaktor kedua, ini luas persegi panjangnya adalah 0,8 kurangi 0,4 ya. Sumbu X-nya, kemudian sumbu Y-nya adalah 800 ya. Jadi 800 dikali dengan 0,8 kurangi 0,4. Jadi kalau pertanyaannya adalah hitunglah total volume 2 reaktor, jadi yang Anda lakukan adalah Anda hitung volume reaktor yang pertama, kemudian ditambahkan dengan volume reaktor yang kedua. Jadi total volume reaktornya di sini adalah sama dengan P1 plus P2 atau 364 liter. Ya. Jadi kalau kita bandingkan misalkan satu reaktor CSTR, langsung kita gunakan untuk mencapai konversi 80%, kemudian kita bandingkan dengan menggunakan 2 reaktor CSTR, ya, di mana konversi akhirnya sama-sama 80%, tetapi konversi intermediate-nya atau konversi yang keluar dari reaktor pertama adalah 40%, maka kita lihat total volume reaktor yang dibutuhkan adalah ternyata yang reaktor CSTR seri itu membutuhkan volume reaktor yang lebih kecil dibandingkan dengan kalau kita menggunakan satu reaktor CSTR yang langsung mencapai konversi 80%. Jadi artinya untuk kasus ini kita berkesimpulan bahwa reaktor CSTR seri itu lebih ekonomis dibandingkan dengan menggunakan satu reaktor CSTR tunggal. Ya. Kemudian pertanyaan berikutnya, dengan menggunakan data yang sama, kita diminta untuk menghitung dan bandingkan volume total kedua skema reaktor seri di atas jika diinginkan konversi intermediate-nya adalah 50%. Jadi diketahui X2-nya 0,8, sama-sama 0,8, tetapi X1-nya adalah 50%. Ya. Maka yang kita lakukan adalah kita coba bandingkan ya, kita hitung total volume di skema yang A, kemudian kita bandingkan dengan total volume untuk yang skema B. Ya. Nah, untuk skema A itu yang pertama adalah reaktor PFR, diikuti dengan reaktor CSTR, atau kalau kita gambarkan dalam skema yang ada di kurva laju reaksi versus konversi, itu bentuknya seperti ini. Jadi pertama PFR kita set sampai 0,5, kemudian CSTR-nya dari 0,5 sampai 0,8. Nah, tentunya untuk yang PFR, ini kita menggunakan metode Simpson. Ya. Sini ada berarti ada berapa ini? Ini kalau 0 sampai 0,5, kemudian intervalnya adalah kita buat 0,1, berarti ada sekitar 1, 2, 3, 4, 5, 6. 6 data ya. Ada 6 data. Berarti kalau 6 data kita menggunakan rumus seperti ini. Ya. Atau mau dibuat jadi 3 data juga bisa ya. Jadi 0, 0,25 dan 0,5 mungkin lebih simpel ya. Jadi kita buat intervalnya adalah 0,25 sehingga di sini kita punya 3 data yaitu data pada X sama dengan 0, X sama dengan 0,25 dan X sama dengan 0,5. Ini kita masukkan ke dalam persamaan ya, delta X per 3 jadi 0,25 dibagi 3 kemudian dikalikan dengan superminer A pada X sama dengan 0, plus 4 kali superminer A pada X sama dengan 0,25, kemudian plus superminer A pada X sama dengan 0,5. Kemudian setelah dihitung, ini ketemunya 97 liter. Kemudian yang skema kedua, kita lihat di sini untuk yang CSTR, itu ini artinya 0,8 kurangi 0,5, itu sama dengan 0,3, dikalikan dengan 800, ya. Jadi 0,3 kali 800, kemudian kali FA0, ketemu volumenya adalah 208 liter. Sehingga volume total untuk skema A itu sama dengan 97 plus 208 atau 305 liter. Ya. Itu yang skema A. Sekarang kita bandingkan dengan skema B. Skema B itu adalah posisinya yang pertama adalah CSTR, kemudian yang kedua adalah PFR. Untuk yang CSTR di sini konversi X1-nya adalah 0,5, sementara di PFR X2-nya adalah 0,8. Di sini kita gambarkan untuk yang CSTR itu artinya persegi panjang dari 0 sampai 0,5 ini. Sementara yang PFR dari 0,5 sampai 0,8 ini artinya kita hitung luas area di bawah kurva. Jadi kita hitung ya menggunakan metode Simpson ya. Ketemu volume totalnya adalah 262 ya, 262 liter. Jadi kalau kita bandingkan dengan total volume yang skema A, kita lihat bahwa volume total skema B itu memberikan volume total yang lebih kecil ya, memberikan volume total yang lebih kecil. Jadi intinya di sini kesimpulan kita minggu lalu ya, di mana kalau kurva laju reaksinya itu adalah cekung seperti ini, kesimpulan minggu lalu adalah kita sebaiknya mempertahankan konsentrasi reaktan di dalam reaktor setinggi mungkin ya. Jadi seharusnya kalau berdasarkan pada kesimpulan kita minggu lalu, artinya untuk skema A dan skema B itu seharusnya mengikuti kesimpulan kita minggu lalu, seharusnya skema A memberikan volume yang lebih kecil. Tetapi dalam perhitungan yang kita lakukan, ternyata skema B di sini memberikan volume yang lebih kecil. Ya. Jadi agak bertolak belakang dengan kesimpulan kita minggu lalu, yang menyatakan bahwa yang PFR itu sebaiknya diletakkan terlebih dahulu. Ya. Tapi di sini kenyataannya yang skema B, CSR-nya lebih duluan itu memberikan volume yang lebih kecil. Nah, kenapa bisa seperti itu? Itu karena posisi dari X1-nya. Ya. Posisi dari X1. Jadi X1 ini adalah konversi intermediate. Jadi kalau konversi intermediate-nya kita ubah, ya, kalau kita ubah misalkan jadi 0,4 ya, seperti yang di sini ya, 0,4 itu ada kemungkinan volume total reaktor yang dibutuhkan itu akan bisa membalikkan keadaan. Tadinya yang skema B volumenya lebih kecil, mungkin saja untuk konversi intermediate 40%, maka skema A bisa saja memberikan volume yang lebih kecil. Sehingga di sini ada kesimpulan bahwa ya ukuran relatif dari reaktor Jadi volume reaktor itu sangat tergantung pada konversi intermediate. Jadi artinya kalau pada reaktor seri seperti ini, maka posisi dari posisi dari X, terutama X1 atau konversi intermediate, itu sangat menentukan total volume yang kita butuhkan kalau kita menggunakan reaktor yang disusun seri. Jadi kebetulan dalam skema yang lebih kecil, walaupun sesuai dengan kesimpulan kita minggu lalu, ini seharusnya yang duluan adalah yang PFR, ya. Jadi artinya di sini selain kesimpulan kita minggu lalu, di sini kita bisa menyimpulkan juga bahwa posisi dari konversi intermediate atau konversi yang keluar pada reaktor yang pertama ataupun kedua, kalau ini misalkan susunan reaktornya ini ada 3 misalkan ya, maka itu posisi dari konversi intermediate sangat menentukan skema reaktor yang akan kita pilih. Jadi sebaiknya kita lakukan apa? Yang kita lakukan adalah kita langsung menganalisa dari kurva laju reaksinya. Nah, kemudian berikutnya kalau misalkan kita punya skema seperti ini, ya. Jadi skemanya misalkan seperti ini, ada 2 skema ya. Satu CSTR, kemudian diikuti PFR, sementara yang satunya adalah PFR diikuti dengan CSTR. Kemudian kita punya kurva laju reaksi bentuknya seperti ini. Jadi ada nilai maksimum, ada nilai minimumnya di sini. Nah, pertanyaannya adalah kalau kita punya sistem seperti yang ditunjukkan oleh gambar ini, gambar yang sebelumnya, ya. Jadi ada CSTR, ada PFR, ya. Kemudian diketahui konversi intermediate-nya 0,3, kemudian konversi akhirnya adalah 0,7. Bagaimana seharusnya reaktor itu disusun supaya menghasilkan volume total yang minimum? Jadi artinya konversi intermediate-nya adalah 0,3 di sini, kemudian konversi akhirnya adalah 0,7. Jadi tanpa melakukan perhitungan kita bisa melihat bahwa kalau kita misalkan menggunakan CSTR di seri dengan PFR, maka kalau CSTR-nya yang posisi pertama, itu artinya di sini X1-nya 0,3, maka di sini volume CSTR-nya adalah ini ya. Ini kita tarik ke atas sampai mendekati puncak, kemudian kita hitung luas area persegi panjang. Sementara untuk yang PFR-nya dari 0,3 sampai 0,7 ya. Dari 0,3 sampai 0,7, karena dia PFR, maka volumenya adalah sama dengan luas area di bawah kurva dari 0,3 sampai 0,7. Itu ya kira-kira ya. Nah, sementara kalau kita menggunakan PFR terlebih dahulu, ya, kemudian diikuti dengan CSTR, jadi PFR diikuti dengan CSTR, maka kalau dia PFR dari 0 sampai 0,3, maka itu sama dengan 0,3, ini kita tarik ke atas, maka volumenya itu setara dengan luas area di bawah kurva dari 0 sampai 0,3. Sementara yang reaktor kedua ya yang adalah reaktor CSTR, maka dari 0,3 sampai 0,7 ini ya. Ini kita tarik dari 0,7 ke sini. Kemudian kita tarik ke kiri sampai 0,3 ya. Maka ini adalah luas persegi panjang yang setara dengan volume reaktor CSTR. Sehingga kalau pertanyaan nomor A adalah kita diminta untuk menentukan susunan reaktor yang mana yang memberikan volume total reaktor yang paling minimal, jawabannya adalah yang skema yang bawah. Ya. Jadi skema yang bawah ini memberikan volume total yang lebih kecil dibandingkan dengan skema yang di atas. Kemudian kalau diketahui misalkan laju alir volumetriknya adalah 50 liter per menit, berapakah total minimum volume reaktornya, ya. Jadi berapakah total minimum reaktornya? Jadi karena kita memilih apa namanya, sudah menentukan bahwa yang susunan yang di bawah ini yang memberikan volume total yang terkecil, maka yang kita lakukan sekarang adalah kita hitung volume reaktornya, ya. Berarti kalau dia CSTR terlebih dahulu, artinya dari 0 sampai 0,3, itu artinya luas area di bawah kurva. Kemudian yang reaktor kedua adalah CSTR, ya. Kita hitung dari 0,3 sampai 0,7, ini luas persegi panjangnya berapa, gitu ya. Kemudian nanti setelah kita hitung, ya, volume reaktor itu sama dengan, ya, laju alir volumetrik dikalikan dengan konsentrasi awal reaktan, ya, kemudian dikalikan dengan entah itu integral dXA per min RA atau XA per min RA, ya. Nah, karena di sini kurva laju reaksinya dinyatakan sumbu Y-nya adalah CA0 per min RA, ya, maka sesuai dengan persamaan desain dari reaktor PFR maupun CSTR, di mana V sama dengan V0, ya, atau laju alir volumetrik awal dikalikan dengan CA0, kemudian dikali kalau dia PFR berarti integral dXA per min RA, sementara untuk yang CSTR berarti XA dibagi min RA. Jadi Anda tinggal hitung luas area di bawah kurva dari 0 sampai 0,3, ya, menggunakan metode Simpson. Kemudian itu nanti dikalikan dengan laju alir volumetrik 50, kemudian ditambah dengan luas persegi panjang dari 0,7 sampai 0,3, kemudian dikalikan laju alir volumetrik. Jadi ketemunya sekitar 750 liter, ya. Jadi itu adalah volume total minimum yang dibutuhkan untuk sistem kalau kita punya satu reaktor CSTR dan satu reaktor PFR, kemudian kita susun secara seri. Jadi kita pilih kombinasinya atau susunannya adalah susunan yang di bawah ini, yaitu PFR diikuti dengan CSTR. Sampai di sini ada pertanyaan?
Pak, saya ingin bertanya, Pak.
Ya.
Tapi ini nggak ada di soal ini sih, Pak. Ini saya kemarin lihat di soal yang Pak Putu sempat share juga, yang soal UAS nomor 1 ya kalau nggak salah, Pak. Yang minggu lalu Pak Putu sempat bahas juga
Ya.
gitu, Pak.
Ya.
Soalnya kan mirip dengan buku Vogler ya, Pak ya. Cuman itu ada tambahannya, kondisinya ketika kita diberikan volumenya terlebih dahulu. Jadi dikasih tahu volumenya CSTR 300 liter dan CSTR 400 liter, kemudian ditanya urutannya 300 liter dulu atau 400 liter dulu agar menghasilkan konversi yang lebih tinggi. Nah,
Ya.
itu kendalanya waktu saya coba kerjain itu saat menentukan intermediate, Pak. Konversi di intermediate. Jadi saya nggak tahu sih ini caranya benar atau enggak, tapi saya pakai trial akhirnya, Pak. Mungkin kurang akurat juga gitu jadinya. Itu salah metode
Ya.
mungkin saya, Pak.
Betul, memang harus pakai trial itu.
Oh iya, Pak. Makasih, Pak.
Ya, betul, memang harus pakai trial ya.
Soalnya
memang
kan
ya.
Oh, ya maaf, Pak. Gimana, Pak?
Nggak apa-apa, silakan.
Oh ya, soalnya kemarin saya coba itu cukup membingungkan sih, Pak, karena ada dua variabel yang kita nggak tahu tapi berhubungan, yaitu konversinya sama min seper RA-nya gitu. Seper min RA, sorry maksudnya. Jadi coba-coba, Pak.
Memang harus di trial yang soal itu ya. Soal UAS
2017-2018, Pak.
2017-2018. Bentar. Seingat saya itu memang harus menggunakan trial. Makanya saya ini letakkan soalnya di nomor E ya, paling akhir karena memang sedikit lebih sulit dibandingkan dengan yang soal-soal yang nomor A sampai nomor D ya.
Mungkin kalau trial apa ada metode trialnya gitu Pak. Jadi kalau saya sih trialnya
Ya,
coba-coba Pak, benar-benar trial error gitu Pak.
betul. Jadi memang tidak ada apa namanya, tidak ada metode yang khusus ya. Yang E ini maksudnya ya.
Iya Pak, betul Pak.
Nah, ini memang harus trial dan butuh waktu memang ya untuk trialnya. Saya sendiri juga lupa nih jawabannya berapa ini ya. Tahun 2000 berapa? 2017 ya. Ya, ini memang harus di trial. Harus di trial
Iya
memang.
Pak.
Ya.
Kalau saya coba sih yang 300 liter lebih duluan itu konversi akhirnya 0,33, kalau yang 400 liter dulu 0,32 ya. Mungkin ada kurang teliti dari saya juga bisa jadi Pak waktu trial Pak. Kan baca
Ya.
grafik juga soalnya.
Ya, betul. Betul. Tapi tenang aja kalau soal seperti ini biasanya saya toleransinya agak tinggi ya. Jadi artinya ini memang perlu trial. Jadi yang penting nanti waktu menulis jawaban itu dijelaskan aja step-stepnya ya. Karena dari step yang Anda tuliskan itu artinya saya bisa menilai kira-kira Anda paham nggak maksud soal ini gitu ya. Jadi jangan langsung jangan langsung tuliskan jawabannya langsung, tapi perlu ada penjelasan sedikit lah ya supaya nilainya bisa full house atau maksimum ya. Ini memang pakai trial ini Feren, seingat saya. Karena kalau
Iya
nggak
Pak,
trial,
makasih Pak.
ya nggak di trial nggak bisa ini. Ini 2017 berarti ini saya baru pulang sekolah ini Feren. Baru
Masih
disuruh.
hangat ilmunya ya Pak ya. Jadi susah soalnya.
jadi idealisme saya ini masih cukup tinggi ya. Jadi mungkin yang E ini memang saya buat susah banget memang. Hanya beberapa orang yang bisa jawab. Jadi setelah 2017 ini rasanya saya belum pernah mengeluarkan soal yang seperti ini lagi rasanya. Jadi moral of the story adalah jangan khawatir.
Jangan keluarkan soal itu mungkin Pak, moralnya Pak.
Oke, sarannya ditampung ya Beren ya.
Makasih Pak. Soalnya saya pusing coba yang kemarin.
Tapi nanti yang pasti saya ujikan adalah karena sesuai dengan ini ya, sesuai dengan tujuan dari materi sesudah UAS itu adalah cara Anda untuk menginterpretasi data ya. Jadi misalkan ini ya, kalau datanya misalkan yang diberikan itu adalah min XA versus min RA gitu misalkan. Nah, kadang-kadang ada mahasiswa itu langsung diantem gitu, ini langsung diplot gitu. Itu kan keliru ya, atau mungkin bukan keliru lah ya, mempersulit diri jadinya. Jadi artinya kalau langsung diplot artinya kan dia nggak mikir gitu maksudnya. Padahal kan sebenarnya ada cara yang lebih gampang yaitu misalkan ini dihitung dulu sepermin RA gitu misalkan. Nah itu mungkin level yang ingin saya ujikan itu yang seperti itu ya. Kalau saya lihat memang yang materi sesudah UTS itu materinya tidak sebanyak yang sebelum UTS ya. Tetapi level analisanya yang sesudah UTS itu lebih tinggi memang ya dibandingkan dengan yang sebelum UTS. Karena yang sebelum UTS itu kan kita biasanya langsung langsung interpretasi data, sudah punya data, tinggal nanti cocokkan dengan rumus yang mana. Tapi kalau yang sesudah UTS ini kan kita harus analisa soalnya dulu, ini apakah masuk kategori yang mana, baru nanti kita bisa mulai mikir nanti kira-kira ngerjainnya dari mana gitu. Seingat saya nggak share soal itu deh minggu lalu ya. Kamu dapat soal dari mana itu?
Kemarin Pak Putu yang bilang nih silakan di
Saya.
screenshot aja ya, mungkin buat latihan gitu
Oke.
Pak. Jadi saya coba.
Oh ya, sorry, ya, saya lupa soalnya. Ini juga silakan di screenshot juga nggak apa-apa yang soal quiz ini ya. Ini saya tayangkan. Ini ada soal quiz juga mungkin bagus juga untuk latihan soal ya. Ini tahun 2018-2019. Ya, tipikal soal saya sih biasanya kurang lebih sama ya. Jadi yang saya tuntut dari Anda itu waktu UAS adalah yang pasti nanti ada kurang lebih soal seperti ini gitu ya. Yang pasti nggak sama persis dengan ini gitu ya. Ya kurang lebih nanti yang perlu Anda siapkan itu adalah kertas grafik ya. Anda tunjukkan di kertas grafik. Kemudian nanti yang biasanya saya variasikan itu di sini biasanya ya, di soal-soalnya. Ini kan tipikal soal sesudah UTS kan seperti ini ya. Nah, kalau yang nomor 1 ini sebenarnya kurang lebih sama sebenarnya dengan soal UAS yang pernah saya bahas ya. Jadi di sini Anda harus tujuan saya membuat soal yang nomor 1 ini adalah supaya Anda relate atau menghubungkan materi sesudah UTS dengan yang sebelum UTS. Karena yang sebelum UTS itu kan kita belajar tentang laju reaksi ya, persamaan laju reaksi. Jadi bagaimana mencari K, bagaimana mencari order reaksi. Nah, nanti K sama order reaksinya itu nanti kita pakai pada desain reaktor ya. Jadi tujuan saya memang menguji Anda, bisa nggak kira-kira Anda itu relate dengan materi sebelum UTS, kemudian Anda pakai konsep yang sebelum UTS untuk mendesain reaktor di sesudah UTS. Kira-kira seperti itu ya. Nah, minggu depan itu kan saya kosong ya, nggak bisa ngajar karena ada visitasi akreditasi. Jadi mungkin nanti saya akan pakai kelasnya responsi ya. Nah, waktu kelas responsi itu apakah ada yang berhalangan untuk hadir? Ada yang bentrok dengan kuliah yang lain? Itu responsi hari apa ya? Selasa ya?
Iya, jam 1 Pak.
Selasa jam 1 ya. Selasa jam 1 berarti rencana saya sih itu nanti mau saya pakai untuk kuis ya. Kira-kira ada yang berhalangan nggak?
Maaf Pak Putu, saya hari Selasa besok nggak bisa Pak.
Selasa bukan besok, yang minggu ke 14-nya, minggu ke 14 berarti ya. Minggu ke terakhir berarti dia.
Oh iya, soalnya biasanya saya hari Selasa itu ada check up Pak buat jadi saya. Jadi check up-nya tuh hari Selasa jam 1.
Ada apa?
Harus kontrol ke dokter Pak.
Oh, oke. Selain dia siapa yang ini? Kalau enggak nanti untuk dia berarti nanti susulan aja kuisnya. Itu gimana?
Oh iya, nggak apa-apa Pak kalau memang itu.
Gitu aja ya. Jadi minggu depan berarti kuliahnya kosong di Jumat ya. Kemudian nanti minggu depannya lagi hari Selasa itu saya pakai untuk kuis. Nah, kemudian minggu terakhir Itu nanti Jumat minggu terakhir itu nanti saya pakai untuk menjelaskan tentang reaktor recycle sedikit ya. Baik, saya kira untuk hari ini mungkin cukup sampai di sini. Kira-kira ada pertanyaan lagi? Kalau tidak ada pertanyaan, kuliahnya saya cukupkan sampai di sini. Terima kasih, selamat siang.
Terima kasih, Pak.
Terima kasih, Pak.
Makasih, Pak.
Makasih, Pak.
Terima kasih, Pak.
Terima kasih, Pak.
Makasih, Pak.